Previously, when solving absorption and stripping problems, we assumed that the solute was dilute enough, such that when it transferred between the liquid and the vapor phases, it wouldn't affect either solvent flow rates. In today's video, I'm going to show you how to deal with it if the solute was concentrated enough such that the transfer from one phase to the other would affect both solvent flow rates. The strategy here is to, instead of keeping track of overall flow rates, we want to keep track of the solute-free flow rates. Here's what I mean by a solute-free flow rate. Let's say that we have a vapor stream that flows at 100 moles per minute. And let's say we have a very concentrated mole fraction. Let's say our Y incoming is 10%. That means that of that 100 moles per minute, that 10 moles is going to be the solute, and the other 90 moles is going to be the bulk gas. And that other 90 moles is what I'm talking about. That is what we want to keep track of. Even if that other 10 moles transfers from the vapor to the liquid phase, we're still going to have 90 moles of the bulk gas. So the formula for solute-free flow rates is going to be V prime is the letter in L prime. So this is defined as the solute-free vapor flow rate. And L prime is defined as the solute-free liquid flow rate. So remember, for absorption stripping, we have three components in the system. We have the solute, the bulk vapor, and the bulk liquid. So in previous examples, we've had air, water, and some type of solute systems. The mathematical formula for V prime is going to be equal to 1 minus the vapor phase composition of solute times the overall flow rate. And that should make sense, right? So even though there's three components within the system, each stream only contains maximum of two things, because we are still going to assume that vapor does not condense and liquid does not vaporize. So again, this formula should make sense. So 1 minus Y, remember Y is the mass fraction or the mole fraction of the solute. Therefore, 1 minus Y would be the mole fraction of the other stuff, the bulk. So therefore, 1 minus Y, the mole fraction of the bulk vapor times the overall vapor flow rate would be equal to the solute-free vapor flow rate. Similar thing for the solute-free liquid flow rate. This is going to be 1 minus X times L. And the beauty of this method is that just like in the dilute case, the solute-free flow rates are going to remain unchanged throughout the column. In other words, I can make the following relationships. I can say that L prime in is equal to L prime out, and V prime in is equal to V prime out. And this is regardless of what the solute mole fraction actually is. That's why we call it solute-free flow rates, because it doesn't take into account what the mole fraction of the solute is. Now, the other side of this is that I also have to define solute-free mole fractions. These solute-free mole fractions are defined as follows. Big Y is equal to little y over 1 minus little y, and big X is equal to little x over 1 minus little x. Just as a quick note for my handwriting, because sometimes these letters can be difficult to distinguish between the big and little. My handwriting, the big Y just looks like a regular little Y, and my little y kind of looks like a cursive Y. Similar thing for my X. For a big X, I just draw a big cross, and my little x is more of like the cursive math type little x that you'll see. So solute-free mole fractions are a little bit more difficult to understand conceptually, but the reason why we have to define them is because when we do the material balance, this is what we need. So for example, let's take just a regular column problem where I've got V, Y in, V out, Y out, L in, X in, and L out, X out. Now my overall material balance, remember, is V in, Y in, plus L in, X in, equals V out, Y out, plus L out, little x out. These are all little variables, by the way. How is this going to translate then into solute-free flows? So if I draw the same diagram again, but now instead of the regular flow rates, what if I wanted to make them solute-free flow rates? So once again, instead of labeling V out, I'm going to label V prime out, big Y out, L prime in, big X in, L prime out, big X out, and V prime in, big Y in. Now my material balance, I want it to look the same as it does. And the reason why I've defined the solute-free mole fractions is so that my material balance looks the same. So it's going to be V prime in. Remember, V prime in and V prime out is the same thing. So I'm just keeping the subscripts for clarity, but you can drop these if you'd like. V prime in times big Y in plus L prime in times big X in is equal to V prime out, big Y out, plus L prime out, big X out. And remember again the definitions of these variables. So just for example, L prime in was defined above to be 1 minus little x times L, and big X is defined to be little x over 1 minus little x. So if you take these definitions, the 1 minus little x is going to cancel. L prime times big X is equal to L times little x. So once again, that's why we define solute-free mole fractions, so that my material balance can now be written in terms of the solute-free variables. And if you do it like this, you can easily start to see the analogy. So because my material balance is unchanged, my operating line is also going to be unchanged. With the exception, of course, that instead of the regular variables, they're going to be solute-free variables. So once again, here are those operating line equations, which you'll notice are the same exact form as the operating lines that I've derived before, only with the solute-free versions of the variables that are replacing the regular variables. And just to define these one more time, remember these are the two forms of the operating lines, and you should choose whichever one is more appropriate for your particular problem. And once again, anytime I say operating line, I mean derived from a material balance. Okay, so that's settled for the solute-free version. However, we still have the issue of dealing with the equilibrium data. And the issue here is that our equilibrium relationship doesn't change. It cannot change. So remember that from before was that y of stage n is in equilibrium with the x that comes off of stage n as well. This is our equilibrium relationship. It is improper to simply replace my solute-free variables with these variables. So therefore, what I have to do is I have to write little y in terms of big Y and little x in terms of big X. So it's big Y over 1 plus big Y is equal to h over p times big X over 1 plus big X. And you can derive these relationships by looking at what I've defined above. So if I rearrange this to solve for little y, right, I get big Y times 1 minus little y is equal to little y. And one more step is big Y minus big Y little y equals little y. Take this term over to the other side and factor out a little y. Little y 1 plus big Y is equal to big Y. And finally, little y is big Y over 1 plus big Y. So you can do that for both variables and get this relationship. And this is now what our equilibrium relationship has become. All right, so this might look strange. Why have I written it like this? So what I recommend, first of all, is that you use Excel as a quick way to convert little mole fractions to big mole fractions. But the problem with equilibrium data is that, once again, I can't write it in terms of the big variables because the equilibrium relationship is only for the little variables. And the reason why I want to write the equilibrium relationship in terms of the solute-free version is because my solution procedure graphically is going to follow the same exact procedure as before. Although instead of plotting little y versus little x, I'm now simply going to plot big Y versus big X. So my procedure would appear as follows. So step one in solving a problem is to convert given flow rates, given entering and exiting flow rates, because that's what you're likely to have in an absorption or stripping problem, exiting flows and compositions into solute-free versions. Then I would plot the operating line on a graph of big Y versus big X. Then I would plot the equilibrium data. And I would do it with converting the little variables to big X in Excel. Plot equilibrium data. Making sure to convert little y to big Y and little x to big X. And step 4 is I step stages exactly as before. And if you've done it right, we should still have a linear operating line. Now the equilibrium data is going to be slightly curved, but depending on what range of data you're looking at, you may not notice it. So equilibrium data may have slight curve. Data may be slightly curved. And I just note that just so that you don't become freaked out when you see it. Maybe slightly curved. And that is because we're switching the coordinates. We're plotting big Y versus big X. The operating line should still be very straight. So this would be for an absorption problem. You would still start on the operating line, go to the equilibrium data, and you would end on the operating line as well, counting the stages by the times you step on the equilibrium data line. So that's all for the theory video. Coming up, I've got a couple of videos that are going to take the same problem that I solved last time and just redo it for different numbers for the concentrated system.